Hello students, today we are going to discuss chapter number 4, that is Insight to Program Execution. In previous class we have discussed about operating system as a resource manager, in which we have discussed about how the operating system manages the different resources in a computer. In this class we will be discussing about the practical portions of this. So we'll be seeing an example about how operating system helps in managing the different resources. So operating system as a resource manager. Example number 1. If CPU is working on a job that requires 10 milliseconds to compute, and after 7 milliseconds the job requires input-output operation which takes 8 milliseconds, thus after 7 milliseconds CPU has to sit idle for 8 milliseconds and rest 3 milliseconds to compute the job. So CPU completed one job in 18 milliseconds. So we'll look into deep about how the CPU is executing over here the process. So if CPU is working on a job that requires 10 milliseconds to compute, that means we are having a job and we are giving the job to CPU to execute. Okay, so the overall time that the CPU takes to compute that job is 10 milliseconds. Okay, so this is your first part. Okay, so CPU is taking around 10 milliseconds to compute that job. Now here comes the inner part of it. After 7 milliseconds the job requires input-output operation. That means while computing this job, first 7.5 seconds, that means 7 milliseconds, the job has been done successfully, and after 7 milliseconds it is asking for input and output operation. Okay, so this input and output operation is being carried out by another part of the CPU. Okay, that is ALU unit and any other or other units that perform input output operations. So the time taken by that input and output unit will be different from the time given for the job to execute. That means input output operation will be taking 8 milliseconds to execute. Okay, so after 7 milliseconds 8 milliseconds will be taken by the input output operation unit. Okay, till the input output operation has been completed, the CPU will be sitting idle. Okay, pay attention here. First is the overall time taken by the job to compute is 10 milliseconds. After 7 milliseconds the job is requiring input and output operation. That input and output operation will be taking another 8 milliseconds. Okay, till this 8 milliseconds the CPU has to sit idle. Okay, because CPU does not have any other job to execute, therefore CPU will be sitting idle. And after this input and output operation is being completed, then we are remaining here with 3 milliseconds. Okay, first 7 milliseconds has been done, another 3 milliseconds have been remaining, so that 3 milliseconds will be taken to complete the job. So in total it is taking 18 milliseconds to complete one job. That means here you can see this 7 milliseconds plus 3 milliseconds, this is equal to 10, and this 8 milliseconds which requires to perform the input and output operation. So while adding this 7 plus 8 plus 3, which is giving us 18 milliseconds. So the CPU is taking 18 milliseconds to compute only one job at a time. Okay, so this is here first example. Now coming to the next example, that is as soon as CPU is seen idle, then immediately operating system loads another process which requires 7 milliseconds to compute. So rather than to sit idle, the CPU works on second job and then gets back with the first job. In this case CPU was able to compute two jobs in 18 milliseconds. So what happens in the second example here is, while in the previous case the CPU was sitting idle when the job went for input and output operation. Okay, during the job's input and output operation CPU was sitting idle. Okay, when CPU was sitting idle, then the operating system has noticed that the CPU is sitting idle and it is loading, that means operating system will load another job to the CPU. Okay, this is your second example. Okay, in second example, what happens is when operating system is seeing that CPU is sitting idle, then immediately it will be assigning another job to that CPU, so that the CPU does not sit idle and works continuously. Okay, so once CPU is sitting idle, another job is being assigned to it, and once the input and output operation has been completed, the previous one, okay, once the previous one's input and output operation is completed, then the CPU will switch over to the first one, and then it will complete the job and then come back to the second job. Okay, so simultaneously it will be working with two jobs at a time. Okay, therefore the CPU is saving time and it was able to complete two jobs in 18 milliseconds. Okay, so here you can see throughput equal to number of job completed upon time taken. So throughput is nothing but your computer's efficiency. Computer's efficiency means how much job is completed in the given time. Okay, so in the first case, throughput is one job in 18 milliseconds, which is not a good thing. In second case, throughput is two jobs per 18 milliseconds. So as compared to the first one, it is good. Okay, so this is how the operating system acts as a resource manager. Coming to the next one. Thus, we can say that by loading multiple processes, the operating system improves the overall performance of the computer system. When multiple processes are running simultaneously, it is important to manage them. For this purpose, OS provides following functions: process management, process scheduling, memory management, and input and output management. So we'll be discussing this. Thus, we can say that by loading multiple processes, the operating system improves the overall performance of the computer system. This means that when the CPU is working on the job, that means for example it is doing the first job, and if the CPU is seen idle, then immediately what operating system does is it will load another job to the CPU. So by doing this, the computer's efficiency is increased. That means the performance will be increased, and once the performance is increased, the computer will work good. So when multiple processes are running simultaneously, it is important to manage them. Okay, so once more than one program or a job is being executing in the CPU, then it is important to manage the different jobs, because there is a chance of being clashing between the two different jobs or many other reasons. So in order to avoid that, there are different functions, okay, in the way operating system manages them. So here are some functions how operating system functions as: process management, process scheduling, memory management, and IO management. So these are the four functions with which the operating system helps to manage the different jobs at the same time. So why do we need these functions to manage? We need these functions to manage because, for example, in previous one, in first example, what it happens was, when the first job is executing, then it will wait until and unless every operation is not completed. Okay, so in that case, there is no other job interfering in the first job, and therefore the job will be executed finally. But when we come to the second case, when CPU is being sitting idle, then another process is being added to the CPU, so that the CPU does not sit idle and works more efficiently. So there might be chance of being clashing between the two jobs. That means the two different jobs might be clashed together, or the data might be exchanged between these two, or any other things which can happen between these two jobs. And therefore, to avoid these problems, there are different functions which are being provided by operating system so that these two can work simultaneously. So coming to the next one, functions of operating system. Now we'll be discussing each of the functions of operating system individually. First, process management, process scheduling by operating system, memory management and IO management. So let us discuss the first one, that is process management. When a program needs to be executed, it approaches operating system. This means that when a program is needed to be executed, that means whenever you want a program to be executed, then it approaches to the operating system. Okay, so what happens when we open any program? Then the program will be directly going to the operating system. It will be approaching to the operating system. Okay, so coming to the next one, the process scheduler of operating system loads it into memory and it becomes process, which is executed as per instruction. Okay, so once the program is being approaching to the operating system, then now it is the function of operating system to do something. So what operating system will do? The process scheduler of operating system, that means the process scheduler is there in the operating system. The function of this process scheduler is it will load it into memory and it will become a process, and then it is executed as per the instructions. Okay, so what is the role of process management? The role of process management is that it will load the process into the memory and it becomes a process further, which is executed as per the instruction. Tasks during process management. There are different tasks that are available during the process management. They are allocation of memory, states of process and process control block, that is PCB. So firstly, we'll be discussing about allocation of memory. In this section, the process is assigned with different sections of memory for proper execution. By the name itself, you can understand that the process will be assigned different sections of memory for proper execution. That means the memory is a very huge place, and in that memory, it will be, that means the process will be given different sections, okay, so that it can execute properly. First part is given to hold the compiled code of program. So here we will be seeing the different sections, how the program is being, how the job is being given different sections. So first part is given to hold the compiled code of program. Okay, so the first part of memory, okay, the first part of memory will be given the compiled code. Second part is given to store the global variables of the program. Okay, so once in the first part what happens is it will be containing the compiled code. In the second part, all the global variables of the program will be stored. Okay, so first part and second part have been completed. Now third part is known as a stack. Stack is used to hold the return addresses of function calls, arguments passed to the function, etc. So here third part is known as a stack. So a stack is nothing but a process in which all the things are being arranged. For example, you can see how the plates are arranged in a table whenever they are served in the party. Okay, so you might have seen the plates have been stacked one after another. So that is known as a stack. Or else you can see how the books are stacked in the library. So that is the best example of a stack. So in a stack what happens is all the items will be placed one after the another in a uniform way. So third part is known as a stack. This stack is used to hold the return addresses of function calls, pass arguments and functions, etc. Fourth part is heap memory area. From here, the chunks of memory are allocated via processes dynamic memory allocation function. So here, fourth part is the heap memory area. Heap memory area means the part of memory from where the small parts of memory can be taken and then that are assigned to different processes via dynamic memory allocation function. Okay, by using dynamic memory allocation function, the memory taken from the heap memory will be assigned some processes. Okay, so here you can see in the figure this conceptual memory map of a process. Here you can see the first part is over here, the program code. Okay, the first part of memory will be containing the program code. Second part will be containing all the global variables which have been defined in the program. Here you might notice this stack and heap. Here third number is stack and fourth number is heap. So here the location is as it is given in the picture. So do not forget the 4 is the middle one and third is the upper one. So what happens in stack? Stack is used to hold the return addresses of function calls, arguments passed to the functions and etc. Heap. This area is used for dynamic allocation of memory. So this is what is happening in allocation of memory. Coming to the next one, that is states of process. States of process. By the name itself we can understand that the process will be having some different states. So when a program is ready to be executed, it is loaded in memory, that is start, and it becomes the active process. That means whenever a program is ready to be executed, then it is loaded into the memory and therefore it becomes an active process, and this is known as the start. Following are different states of process: start state, ready state, running state, wait state and exit. So these are the 5 different states of processes. First, start state. The initial state where process is started by loading program in the memory. So start state is the initial state, okay, where process is started by loading program in the memory. Okay, whenever the program is being loaded to the memory, then it is known as the start state. Ready state. When program is loaded in memory and is ready to be executed, then it has to wait for CPU, as CPU might be executing other jobs. This is the ready state of process. So in short, you can say when the program is ready to be job is ready to be executed and it is being waiting for the CPU so that CPU completes its previous job and attends this job. So this is known as the ready state. In ready state, what happens is the the program which is being loaded into the memory, it is waiting for the CPU to execute it. Okay. Third, running state. Once the process gets CPU time, the CPU starts executing the instructions of the process. Okay. So once the process gets CPU time, that means once the CPU is giving time to this process, then the CPU starts executing the instructions of the process. That means there are instructions in the process, and once it is being loaded into memory and then to CPU, then the instructions in that process will be executed. This is the running state of process. Wait state. If during execution the process has to wait for some resource, then the CPU takes up another process, that is ready state. Waiting for CPU and the current process state becomes waiting state. Once all the resources are available, that is input of file etc., its state will then change to ready state, that CPU can execute it again. Exit state. Once all instructions are executed successfully, then it is terminated by operating system. Therefore, the state is now changed to terminated or exit state. Finally, the process is removed from the memory. So these are the different states of process which are available. So I hope you are clear with this states of process, allocation of memory, and the first basic part of this process management. So in the next class we'll be discussing about the diagram of the states of process and process control block in brief. So I hope you are clear with all the topics we have discussed today. Okay, till then, thank you.